Good morning, everyone. We all having a great day here so far? Yes? Woo, woo. All right. What, are you going to go back to the hotel and take a nap? Come on. All right, there we go. Awesome. So our first talk today, well, I guess our first non-keynote talk today, is by Amy Hanlon. She is an engineer at Venmo, and she's an alum of the Recurse Center, and she's going to be talking to us about investigating Python Wats. I hope I pronounced that properly.
Hello. Can you hear me? Cool. So like you said, I am Amy Hanlon, and today I'd like to investigate some Python Wats with you. I work at Venmo as an engineer. I am also an alum of the Recurse Center, which you might know instead as Hacker School. And here's where you can find me on the internet. So first, let's talk about what is a Wat. What do I mean by this thing? So really what I mean is a surprising or unexpected behavior in Python. Some people might call them gotchas. Quick show of hands here, who has seen Gary Bernhardt's Wat lightning talk? Great. Okay, so you're exactly the kind of people that I want to talk to. If you haven't, that's totally okay too, not a prerequisite, but it takes like 4 minutes to watch, and I highly recommend it. So for this talk, what I want to do is go over some of these sort of like classic surprising behaviors in Python that might cause bugs in your programs when you are new to the language, and really spend the time investigating why they happen. So the surprising behaviors that I will go over today can be loosely grouped into 3 categories: identity, meaning object identity, mutability, and scope. So first, let's talk about object identity. And we're going to illustrate this with a few examples to start out with. So let's do a bit of trivia. Hopefully we can make this interactive. So let's try with the example. We fire up our trusty CPython interpreter, and we type in 3 different lines: A equals 256, B also equals 256, and then we ask A is B. Show of hands here, who thinks that this will evaluate to true? Cool. And who thinks it will evaluate to false? Great, 50-50. So like some of you might learn something today, which is great. True. Cool. Maybe this is surprising. I guess to half of you it might be. Let's do another quick example. So what if we say instead 257? So the only difference between this slide is that we went 1 number bigger. So we're still in the CPython interpreter. The first line we say A equals 257, second line B equals 257, and then we ask A is B. Raise your hand if you think it'll be true. I think maybe I gave it away. So raise your hand if you think it'll be false. Yeah, so this is false. So like, what? Really? I don't have any images of Darth Vader like getting water out of the ocean and filtering it, but hopefully it'll still be fun regardless. So this is weird, right? So let's take a minute to really investigate what's happening here. So this example is actually a quirk of the CPython implementation of Python. Some implementations behave a bit differently. But when you fire up your trusty CPython interpreter, before you're even given your prompt, the interpreter will create an array containing the integers between -5 and 256. So these are kind of interned in a sense. So when you write a statement like A equals 257, that's binding the name A to the integer value 256, that has already been stored in memory for you in this array of integers. So it does this rather than creating a new integer object, which you might expect. So then when you type B equals 256, the interpreter is smart enough to know that it already has this number stored in this array that it created for you when you started the Python interpreter. So you bind the name B to this same integer 256 in that array. So then when we type in A is B, this evaluates to true, because is really testing for object identity. Is this the exact same object that's stored in memory? For the 257 example, this happens to be outside of the array of integers that we initialize when we start the interpreter. So we create a new instance of the integer class, give it the value 257, and store it in a different place in memory. And then when we type B equals 257, the interpreter isn't smart enough at this point to know that we've already created an integer of the value 257. So we create a new one, we also store that in memory, and we bind the name A to it. So when we type A is B, this evaluates to false because they're two different objects stored in memory, even though they happen to have the same value. So let's do another example. What if on the same line in the interpreter, we type A equals 257 and B equals 257, and then we ask A is B? Raise your hand if you think this will be true. Cool. Raise your hand if, oh no, I gave it away. Okay, it's all right, it's all right. It is true. Some of you were right. I don't know if the others in the audience were hesitant or thought it would be false, but that's okay. I'll just default to you learning something, which is good. Okay, so when they're defined on a separate line, let's look at these like two examples side by side. When they're defined on separate lines, then A is B evaluates to false, and when they're defined on the same line, A is B evaluates to true. What? Right? What's going on here? So let's talk about code objects to really illustrate this example. When you type a line of code in the interpreter, press enter, and you get your prompt back, that means the interpreter has compiled a code object for you. So we can get a handle on this code object by defining our source code in a string and then using the built-in function compile. And this will return a code object for us. We pass it some arguments like our source code, also file name and mode, but let's not focus on those. So now that we have a handle on this code object, there are some attributes defined on it. One of those attributes is co_consts, and this is the constants defined in our statement. And the important part here is this first element of the tuple, the 257. The none is just there because it's like the implicit return. Okay, so then when we look at the code object for our second line of code, the B equals 257, we can similarly use the built-in compile function to get a handle on it and look at the constants that are defined inside that code object. And this has another 257 in it. So the main point that I want to illustrate here is that we have two separate code objects. And that means the interpreter has gone through the phase of parsing all the way down to compiling into bytecode these two different lines. And we don't really give the interpreter the chance to optimize between these two different code objects. So when we define everything on the same line, we get one code object. And we can also get a handle on this code object using the compile built-in function. And similarly, we can look at its constants, and there's only one 257 here. So the interpreter has been given a chance to be kind of smart and only create one. Okay, so we covered identity, where we saw how the CPython interpreter stores an array of integers for you when it's initialized, and also how two objects can have the same value but different object identity. Now we're going to talk about mutability. Okay, so suppose we wanted to build a tic-tac-toe board. And we started by creating a representation of a row in the board. And an empty string is going to mean no one has claimed that spot yet on the board. And so we create this row, and really it's just a list of 3 empty strings. And then we'd like our board to be a list containing 3 rows, which we can do by creating a list with 1 row and multiplying it by 3, kind of how we built the row. Cool, so our board looks like this. It's empty, no one has claimed any spaces yet. And the board itself is a list with 3 elements, and each element in this list is a list with 3 elements. So to illustrate that, we can grab the top row of the board by grabbing the first element. And we can grab the top left square of the board by grabbing the first element of the top row. So let's say we want to start playing, and we want player X to claim the top left square. And we can do that by assigning the string X to the top left square. So then when we display the board, what do you think it will look like? Totally reasonable. Like our expectation here is that there's an X in the top left square, right? Only one person has made a move. But I see some of you shaking your head. No, what? X wins. This is like the easiest game of tic-tac-toe ever. Or I guess it's like a matter of perspective, right? Like if we were O, it would be the hardest tic-tac-toe game ever. You could just never win. What? So what's happening here? So here I have a chart, and this is going to sort of be like an abstraction of what's happening in memory. So the first line of code that we type in is row equals this empty string and a list times 3. And what that does is bind the name row to this list containing 3 elements that we're storing in memory. So now when we create a new list board with 3 elements, each of those elements is a reference to the same list that row references. And that's just how like multiplying lists works here. So we have our row, and then we have like the top row of the board, which is board at the index 0, and the middle row, and the bottom row, which is board at the index 2, and they're all pointing to the same thing. So when we modify the first element of the top row and assign it the value x, that's actually, since every row points to the same list, it modifies that whole column of the tic-tac-toe board, and x wins. So one of the ways that this sort of behavior with like lists being mutable objects, but also their like dictionaries and sets, are using mutable objects as a default value for an argument in a function. So let's illustrate that with an example. This is going to be a very practical function called append cat, and it'll take one argument that we'll call L, and it will default to the value of the empty list. So it's a pretty simple function. We just take L, we append cat because we like cats, and then we return the list. So what happens when we call the function append cat once? Any guesses? Cat, yeah, it's a list with cat in it. Like that's pretty straightforward. We would definitely expect that to happen. Okay, what happens if we invoke it a second time? Who thinks we'll get the same output? Show of hands? Nobody, okay. What about different output? Yeah, you're right. 2 cats, there's so many cats. Where are they coming from? How did that happen, right? It'd be totally reasonable to assume that any time we call append cat without any arguments, Python would initialize a new empty list for us to assign to L, but that does not seem to be the case here. So what's going on? Well, in Python, functions are objects, and as a result, they have some attributes assigned or defined on them. And one of those attributes is called defaults, because we're using Python 3. And if we were using Python 2, it would be called func defaults. And we can use these attributes to sort of learn about what's happening in the function from outside of the function body. And sometimes we can do some fun things to the function with them, too. So let's see what's inside this attribute. So right now, before we've invoked append cat, it is a tuple with 1 element, and that's the empty list. So this is the default value of our argument L. So suppose we invoke append cat, and then in the second line, we try looking at the defaults again. We can see what that contains. So now it contains a list with 1 element, cat. So you can kind of get a feel for what's going on here. When Python defines a function with default arguments, it'll store that value when the function is defined inside the defaults. And it doesn't create a new list each time the function is invoked, which you might otherwise expect. So let's try to do like a fun thing here. Sometimes when these kind of internals of Python are exposed to me, it can be a really fun learning exercise to see what bad things you can do with them. So for fun, let's see if we can mutate the default value of L from outside of the function body. So we can get a handle on the default value by using this sort of trick in the Python interpreter, using an underscore character. So that is just bound to the return value of the previous statement in the interpreter. We just get that for free. And we can get a handle on this list containing cat by indexing into the tuple, and then we'll try appending dragon to it. Dragon obviously does not belong in this append cat function, but we'll try. So we try invoking append cat. So who thinks that like we have successfully inserted dragon into this like function? Who thinks it'll like return cat, dragon, cat? Cool. Anyone like not think that this was successful? I kind of gave it away again. Yeah, so cat, dragon, cat. What? And one of the surprising things to me about this is that everyone knows, or maybe not everyone, that tuples are immutable objects. But they can store mutable objects in their elements, and you can like mutate those as you wish. So this is kind of a fun thing that you can do with this like internal that's exposed to us. Great, so we're done talking about mutability, in which we saw how many names can be bound to a single object, even if that object is mutable, and also how mutable default arguments can have some surprising results. So now I'd like us to talk a bit about scope. Let's start by defining a variable a with the value 1. And pretty simple example, we just have this function foo, and it will return a. Okay, so when we invoke foo, two probably reasonable things could happen. One is that it could return 1, and another is that it could result in some like name error, maybe. So what happens when we call foo? Raise your hand if you think it'll return 1. Okay, and raise your hand if you think that it will throw an error. Great. It returns 1. How does this get there, right? So I want to use this to talk a minute about name resolution and how Python will resolve this name a. So when we invoke foo and thus return a, the Python interpreter needs to find what object has been bound to the name a. And it does this by looking in a series of places. First, it looks inside the local scope within the function, and we don't have any assignment statements inside this local scope. So our search for the name a is unsuccessful. Next, we'll look at the enclosing scope. So if foo was maybe a function that was nested inside another function called bar, and bar might have some assignment statements, that would be an example of an enclosing scope, but that's not the case here, so we are also unsuccessful. Next, we'll look inside the global namespace, or global scope, which is the module-level definitions, and inside the interpreter, this a equals 1 is in the global scope. So we are successful here. And we resolve the name a. We know that it's supposed to be the value 1 because that's what it has inside the global scope, and we can return successfully. If we didn't find it there, the last place that we would look is inside the built-ins namespace, and this is what stores built-in names like true, for example, and binds them to their values. We can also see that we're loading an object from the global scope by looking at this function's bytecode. So here we import the dis module from the standard library, which is a bytecode disassembler. And just a note on this bytecode disassembler, it will print out sort of the machine instructions bytecode the interpreter creates in a human-readable form. So when we pass our function foo into this disassembler, we can see this load global instruction. And this is the bytecode instruction for it's pretty straightforward, loading an object from the global namespace. So this is built into the language, like at the bytecode level, we know to look in the global namespace. Let's look at a bit different of an example, and this will be the last example that we'll look at today. What if in foo we tried incrementing a and then returning it? So when we invoke foo, raise your hand if you think that this will return 2. Great. And raise your hand if you think that this will raise an exception. Okay. A bit more uncertainty on this one, which is good. It's a good one to end on. Any guesses to what exception it raises? Python trivia? Yeah, unbound local error. Local variable a referenced before assignment. So what does this mean? It's kind of like a cryptic, like, I don't understand immediately what's supposed to be going on here, so let's investigate a little bit. So from the Python FAQ, there's a statement, when you make an assignment to a variable in a scope, that variable becomes local to that scope. So let's look at this in a slightly different way. What if instead of incrementing a, we had like a very explicit assignment statement, a equals a plus 1? So the a equals part means we're making an assignment inside a scope local to foo. And this makes a local variable inside foo according to the FAQ quote from the previous slide. So we've decided that a is a locally bound name. Then when we try to calculate the value to bind to the name a, we need to figure out a plus 1. And we know that a is bound locally, right? Obviously, we've already decided that. But a isn't defined in the local scope yet. So we get an unbound local error. We can also look at this example, at the bytecode for this example to understand it a bit more. In the previous example, just recall that we use the load global operation to load the value of A from the global scope. So in this example, instead of load global, we use a load fast, which loads the object from the local scope instead. And when this executes, there is no A defined in the local scope yet, so our program fails. We don't even try looking in the global scope for A at this point. So I would like to close with a quote from my friend Rose. Knowledge is power. It's measured in watts. And really, if you would get one thing out of this talk, I'd like for you to be inspired to discover what is really happening when you see unexpected behavior in your programs, because really, every bit of unexpected behavior is a chance for you to learn something new about the language that you choose. And one last thing, if you are interested in bytecode and how the Python interpreter works, plug for my friend, check out Allison Capter's talk, Bytes in the Machine, at 1:40. She demoed it to me last night, and it's great. Thank you.
All right, if we have any questions, go ahead and line up right there behind the microphone center.
Well, the A equals 257 certainly surprised me, but then I had to try it in a Python program, and it does come up as true. So it depends on whether you're using the debugger or whether you're using the actual live interpreter.
Yeah, so that's an interesting point. So when you said you tried it with a Python program, does that mean that you typed those two lines in a module and then ran that through the Python interpreter?
Yes.
Yeah, okay, so this is an interesting point too. A Python module is a code object. So kind of similarly to how in the interpreter we have like two lines, or like when we define them both on the same line of code, that's one code object, and that gives the interpreter the chance to optimize and only create one instance of the integer. A similar thing happens if you just have that in a like .py file and run that through the Python interpreter.
Thank you for answering the unasked but implied question.
You're welcome.
For the mutable default arguments, how do you get the expected behavior?
Sorry, can you repeat your question?
For the mutable default arguments, how do you get the expected behavior of like making?
Oh yeah, absolutely. So there's a pretty common pattern that people will use, and you might have seen it before. Generally, you would default the list value to none, and then at the beginning of your function, check to see if your list is that none value, and if it is, then say the list is the empty list. And that'll force the interpreter to create a new empty list each time you call the function.
Thank you.
You're welcome. Any other questions? Great, thank you. Oh, wait, sorry.
Hold on, one more.
Well, I was just kind of curious. There are the tuples that stored the constant values, and I'm assuming that there's another tuple that maps the argument names to that tuple.
I am not sure about that. I don't think that it stores like the names that way, but I might be wrong. That's a question that I don't know the answer to.
Okay, thank you.
Yeah, you're welcome.
Excellent. Thank you very much, everyone.
Thank you.